Welcome back. Today we're going to talk about how images are data. So just like earlier, we talked about audio and how audio is a type of data we can use where we can go in there and either create audio or modify it or classify it or do different kinds of data science with it. Images are the same sort of idea. So how do we store an image in the computer? Sort of like with the audio, it's an interesting question. And then the answer ends up being just lists of numbers. With audio, if you remember back, it was usually one or two lists of numbers, sometimes more than that for surround sound, but it's a list of the how much pressure there is in the air at any given time. For an image, it's we've got to be able to store colors, and we've got to be able to store it spatially. So for a red block like this, the computer stores it typically in three numbers. So it's a red, a green, and a blue in that order. You'll sometimes hear RGB. That's just red, green, blue. And so for this particular red, it's a 25500, right? You can also write that in hexadecimal. That's the same number, just written a different way. There's color pickers online where you can look at every color and see sort of what's going on. Okay, so now that we've got the computer to recognize, to be able to write down a color as a number, what we need to be able to do is make an image. So for this little smiley face in the upper left, we could blow that up a lot, and we could make basically a grid of colors. So we're zooming in on 3 pixels here. The pixels are the individual squares in the image, right? And the white background there is not actually bright white. It's 93% white. So we have an R, a G, and a B. Then we have something that's kind of a dark color and then a yellow color. And so for each of those, we've got the RGB components. And you could imagine the way this works is basically for each cell, we need to write down the color that's in the cell, and then that's going to give us the whole thing. So to be really explicit about it, you can think of this as stacked images. So in the upper left pixel 00, we have an R, a G, and a B value, a red, a green, and a blue. So what I'm showing here is just the red image. This is the green image. And this is the blue image. And then when we stack all 3 of those up, we get back the original image. So that will give us the image that we're looking for. So this is going to be a little bit more involved for indexing, right? Because you've got your sort of X direction, your Y direction, and then you've got triplets sort of in the Z direction. So it's like a matrix that's actually 3 matrices stacked on top of each other. So each red, green, and blue is an individual matrix. One thing to think a little bit about, we talked about compression before in audio, sort of lossless and lossy compression. It's a little bit easier to think about in images, I think. So let's revisit that. This image here, this red box, is actually a lot of pixels. It's 1.3 million points. So if you were to write this down, you would need 3 values, an R, a G, and a B, for every single point. So you're writing down almost 4 million points to be able to do this. But actually, I can describe the picture in very few words, right? So I could just say, hey, here's the image, here's the size, all the pixels are this. So this is an example of lossless compression, right? I haven't given up anything, I haven't modified it. If I give you that information in the bottom right, you can recreate the image perfectly. Information theory is actually a whole class, a whole group. It's often in electrical engineering. It shows up in other places. I think it's particularly interesting, and I think it's relevant to computer science and worth learning more about. We talked a little bit about the size of images, and we've been talking about them in pixels. There's also stuff about display and resolution. So different displays, you might have heard of like 4K or 1080p or those kind of things. Those refer to the number of pixels, and also some other stuff about how for video, the video encoding is done. This gives you a list of a bunch of different standards. You'll notice some are widescreen, some are not. There's a bunch of things in there. It's also worth noting the density of the pixels changes a lot, right? So some, like cell phones, the pixels are very, very small. Other things, the pixels can actually be very, very large. So it just depends on what you're working with. There's another choice. So we've talked about how many pixels it is, but we also need to choose how to represent the colors. So here is 2 images, and the bottom one is the full resolution original image. The top one is showing what happens when we make that image with only 16 colors. I'm sorry, the bottom one's actually 256 colors. It's not the full original. So you can see with 16 colors, you start to get some interesting patterns. So if you look at the background, instead of being a constant gray, it's actually a dark gray and a light gray sort of patterned in there, right? So there's different ways of compressing this. This is a lossy compression, right? You're saying, hey, I want to represent this image, and I'm only going to use 16 different colors to describe the whole image. That makes it very small, but it also makes it look pretty funny. You could imagine, though, instead of having millions of colors, you only go down to thousands of colors. And for some types of images, for example, a cartoon, that could be great, right? Cartoons tend to have big, flat spaces that are constant color. So that could be really good. While we're on Colorspace, I just want to mention the existence of some other color spaces. So we've been talking about red, green, blue, and that's the most common. In fact, there are other choices. But for red, green, blue, we tend to mix the colors like light. And so when you mix all the colors together, you get white. When you have none of any of the colors, it's black. There's another color space, often called CMYK or CMY, which is cyan, magenta, yellow. And it has the same properties where you can make all the colors from these. Well, let's leave that aside. You can make all the colors you need from that, but they mix more like paint. So you add the different colors together, and they get darker and darker. And with none of the colors, it's white. You'll notice I said CMYK. There's also RGB alpha. Those have to do with transparency. So sometimes you'll want a transparent background or have an image that you can see through a little bit. And that's the alpha or the K channel. All right. So let's talk about doing math on images. Now that we understand that images are just a matrix of colors, we could do some stuff on there. So one thing we could do is standard image processing. And what we're going to do is we're going to take that little matrix. Let's take the one with just a 1 in the middle, and let's run it over the whole image, side to side and up to down. So this is a process called convolution, and we're going to run it over the whole thing. We're going to multiply each time, and then move it one step over, multiply, move one step over, and then when we get to the end of a row, we'll go down a column and start over like a typewriter or something, and then scan through the whole thing again. And we'll take the result of each multiplication and store it in a new image. So when we multiply these, we're actually going to get a scalar out, right? So we're gonna multiply the whole matrix by the whole matrix and get a single number. Well, with this matrix, what we're going to get when we scan over the image is we're going to get the same image back. And the way you can see that is all of the surrounding pixels contribute 0. So we take the pixel we're on, that center pixel, we multiply it by whatever value is there, and then we store it in the new one, right? So that's going to give us back exactly what we put in. which in this case is this strange animal. Right? There's another thing we could do, which is to make the image blurrier. So soft focus or out of focus. And what we're doing here is we're averaging the pixel we're interested in with its neighbors. This is a Gaussian, also called a normal distribution, which you should be seeing in Data Science 10. The 1/16 is just to normalize it. We want this to sum up to 1 so that we don't blow out the image. But so this whole thing will add up to 1. And this is just like a discretized approximation of some blur. So we run that whole thing over the image, and we get this blurrier image out. We can also do sharpening, which is like a edge detection, finding the differences between neighboring pixels. And so here what we've done is we emphasize that center pixel, and then we subtract the immediately adjacent pixels, and we're not doing anything with the diagonals. And here you get this really sharpened image, because what it's looking at is it's saying, hey, what's the difference between this pixel and all of its neighbors? And when that difference is really large, it will boost it up. When the difference is small, it will flatten it down, right? So you get this sort of interesting take on it. In fact, edge detection is a whole more complicated thing. I threw a link to some edge detection stuff. We'll start playing with that a little bit in the class exercise. But obviously, sharpening is not fully edge detection. Edge detection involves a lot more math, and sharpening can often be part of it. There's a bunch of classic image processing, sort of signal processing stuff that's really good. All right. I also want to mention a few more things about how images are stored. So here we've got an image of some soda bottle, and what we've been talking about so far is this bottom image style called a bitmap. And a bitmap is that grid of images, so pixels like you normally think about, and for each pixel you write down the color. But another way to make an image is you could write down the instructions for making it. So you could say, hey, I want a black box. I want it to be this long and this wide. I want it to curve along this way. I want you to have text in this font, right? So you could like write down the pattern for it. That's called a vector graphic, a vector image. And a vector graphic, when we zoom way in, gives us this sort of infinitely sharp resolution because there's, instead of being a list of numbers, it's a list of instructions. You probably won't run into this a ton on the internet. They're around from time to time, but if you make posters or print t-shirts or work with graphic designers, you may see them because when you blow things up a lot, you often want vector images. So I also want to talk about a little bit more about lossy compression. So this may be hard to see depending on what resolution you're watching at, but on the left here, we're seeing an image that we've zoomed way in on, and then an image when we saved it with a lossy method. So each of these characters, right, has a little bit of noise around it. When you save text as an image, that naturally happens because the line is not all the way in one pixel or another, so you get some gray pieces and things. That's totally normal. If you just save that as a bitmap, it would look like the unfuzzed image here. So that's sort of the perfect representation. If you then take that and save it as a lossy type, a certain kinds of lossy types, it can cause this ringing, this fuzziness in the gray space around everything, and that's artifacts that are created by making the image much, much smaller. It can be a little bit hard to understand why making the image smaller would cause noise out in the open space, but what they do basically is they do a thing called wavelet encoding, which is really just like fitting a curve. And they have a small library of curves they can fit from, and so what happens is the curves don't fit perfectly, and so they have some noise out in the other space. This works really good for a lot of natural images, and it tends to work really badly for things like plots or text, because it'll cause this ringing. So there are different lossy formats, and the Colorspace one I talked about is one type. This is another type, and they all have pros and cons. Similarly, you've all seen stuff like this. It happens in Zoom lectures a lot and things, where you get these blocks of color, and this is the same idea where inside each block you can see it's not a pixel. There's some shading in here, but it made a really rough approximation of what's going on, and it doesn't line up with its neighbors. So there's a lot of research in image compression, and these things are called compression artifacts, the stuff that's left over. So this is a whirlwind tour of how images are stored in computers, and really it's just enough to let you know that there are whole classes on this and whole fields. But for us, for data science, what we want to do is know enough to be able to load images and do cool stuff with them. So an early example that did really well is this image recognition, and specifically it's around digit recognition. So digit recognition, the specific example is recognizing zip codes written on postage, on letters. They're handwritten, so it's a pretty hard recognition problem. I have trouble recognizing handwriting sometimes, but it's extremely limited. There's only 10 classes, 10 possible labels, 0 through 9. So you can see some examples in the upper right. Some of them, like maybe this 2 in the bottom row, looks really different than this other 2. And so labeling them correctly seems like it might be a bit of a challenge. It wouldn't be obvious how to write this down. Interestingly, this problem was solved with pretty good accuracy in 1988 with backpropagation. So really similar to the stuff that happens in deep learning. This would be shallow learning, right? So same sort of ideas. It is a neural network, and they were achieving good accuracy. So this plot here is the error. The y-axis is the sort of how much training happened, and you can see in the end they're getting down to very little error. So like 98% accuracy on this data set. Really cool stuff for back then. Nowadays, there's all sorts of things we can do. So one example that gets a lot of press is facial detection and facial recognition. San Diego is in the middle of debating if we should ban the use of facial recognition by police. But there are applications you could think of for facial recognition that are nice, right? I like I use Google Photos, and in Google Photos, I can set it so that with my roommate, anytime I take pictures, those pictures are automatically sent to her. So that can be like a really handy way to share images. There are automatically created endpoints. So you learned requests earlier, which is a way to request data from an API. You can actually post data to an API. So instead of using get, you'd use post, and you can post a picture and get results like this back. So this is I believe a Microsoft API, but many people have one. And you can get all sorts of things, including some like gender that are difficult to classify on images and somewhat controversial, right? About whether or not we should even be doing that from images because of the potential harm it can cause. Obviously, guessing someone's age, that's something that can be difficult to do also. But again, you can think of examples where that would be nice to do. So there's all sorts of stuff you can do in image recognition, and then a lot of it also applies to video, because video is really just sound and moving images, right? So In this class, in the exercises, we're going to go through and do some stuff around image recognition. And in particular, we're going to design a pretty basic Photoshop detection tool. So one that you can present an image to it, and it says, oh, I think this thing's Photoshopped, or, oh, I think this is the original image. So, all right, thanks.